Hello and welcome to lecture number 20 in the course Computer Graphics. We are currently discussing the graphics pipeline, that is the series of stages or steps that has to be performed to convert a 3D description of a scene to a 2D image on a computer screen or on the display that we get to see. So, there are 5 stages as we have already mentioned: object representation, first stage; modeling transformation, second stage; lighting, third stage. These 3 stages we have already discussed completely. Currently, we are in the 4th stage, viewing pipeline, and there will be one more stage, 5th stage, that is scan conversion. Now, the 4th stage, the viewing pipeline, contains a set of substages. The first substage is a transformation from a 3D world coordinate scene description to a 3D view coordinate scene description. Now, this view coordinate is also called eye or camera coordinate system, and this transformation is generally called 3D viewing transformation, which we have already discussed in our earlier lectures. The second stage is projection. So, we project the 3D view coordinate description onto the view plane, and this projection is performed through a transformation which is generally called projection transformation. This also we have discussed in our earlier lectures. There is a third stage in which we perform a mapping or transformation, that is from the view plane we map this to a viewport which is defined on the device coordinate system. This is called window to viewport mapping, where window is on the view plane and viewport is on the device coordinate system. And this third stage we are going to discuss today. Now, before we discuss the mapping, we would discuss one important aspect of projection transformation that we did not discuss in our last lecture, that is the idea of canonical view volume. Let us see what this volume means. As we mentioned earlier, there is an important stage in the graphics pipeline. In fact, this is part of the 4th stage that we are currently discussing, that is viewing pipeline. Here what we do is, whatever objects are outside the view volume are clipped out. Now, that stage is called clipping, and we do it to remove all the objects that are outside the view volume. We already know what is a view volume, that is a region in the 3D space which we want to project. Now, if it involves lots of objects which are partly outside the view volume and partly inside, or lots of objects that are outside the view volume, then we require a large number of calculations to determine which one to clip out, and this involves object surface, view volume, boundary, intersection point calculations. So, where the object surfaces are intersecting with the view volume boundaries. So, if the number is large, then such boundary calculations will be large, and these boundary calculations are not easy. They involve lot of floating point operations, and accordingly the complexity is high. Now, if we have to perform such intersection calculations with respect to arbitrary view volume where we have no control on the boundary planes of the view volume, then this complexity is only to be more. So, we can expect large number of computations which is likely to take large amount of time, reducing the quality of the image, as we will get to see flicker. In order to avoid that, we can use one simple idea, that is, we can come up with a standardized definition of view volume. Irrespective of how the actual view volume looks, we can always convert it to a standardized view volume or a standard view volume. This is called a canonical view volume or CVV in short. So, essentially it is a standard representation of view volume irrespective of the actual nature of the volume. Remember that there are two types of view volumes. One is for parallel projection, that is a rectangular parallel pipe, and the other one is for perspective projection, that is a frustum. Now, both these can be converted to a standard form which we call canonical view volume, which makes the intersection calculations standard and easier to implement. So, for both parallel and perspective projection, the standardized view volume looks the same. However, the way to arrive at the standardized or canonical view volume for both the projections, for the two types of projections, are different. So, let us start with the parallel projection. So, for parallel projection, the canonical view volume that we define is a cube within a specified range, which is -1 to 1 along all the three axes x, y and z. And as I already mentioned, any arbitrary view volume can be transformed to the CVV simply by the scaling operation. So, suppose this is an arbitrary view volume defined in terms of its bounding planes, 6 planes. So, we can always map it by scaling within this range along the x, y, z direction, and correspondingly we get the canonical view volume. In case of perspective projection, this transformation is slightly more complicated, because here we are dealing with a view frustum and we need to convert it to a canonical view volume for parallel projection, that is that rectangular parallel piped, where the x, y and z extents of the bounding planes are within a specified range. So, what we can do here, we will just talk about the idea rather than going into the details. We can convert this arbitrary view frustum to the canonical view volume here by applying shearing and scaling in sequence. As we can guess from the figures that shearing is required to change the shape and scaling is required to change the size. So, when we apply these two transformations on the original view frustum, we get the canonical view volume. Of course, here we will not go into any further details than this basic idea. So, what we have learned, that we define a view volume and this view volume we transform to a canonical view volume, so that in later stages when we perform clipping, the calculations are easier to implement, because we are dealing with a standardized definition of view volume. Let us revisit the sequence of transformations that we perform to project a point P in the world coordinate scene to a point on the view plane. Now, we mentioned that this is akin to taking a photograph, that is, we transfer it to view coordinate system, then take a projection. However, earlier we mentioned these two steps, now one third step is added. So, first we transform the world coordinate point on the view coordinate system, as we have discussed in earlier lecture. And the next step is not projection. Instead, what we do is, in this view coordinate description, we define a view volume, and this view volume is transformed to a canonical view volume, and accordingly the point is also transformed by applying the same set of transformations. So, the next stage is to transform the point in the view volume to a point in the canonical view volume. Then the final stage is to perform the projection transformation, that is, project the point in the canonical view volume on the view plane. So, these three steps, transformation to view coordinate, then transformation to canonical view volume, and then projection transformation, constitute the sequence through which we project a point in the world coordinate scene to a point on the view plane. Mathematically, or in matrix notation that we are following, we can write this series of steps as shown here in this expression, where this transformation represents the transformation to view volume, this one represents the transformation to canonical view volume, and this one represents the projection transformation. Since we are applying them in sequence, so we are following the right to left rule. So, first transformation to view coordinate system, then transformation to canonical view volume, and then transformation to view plane through projection. So, that is the idea of performing projection on the view plane. There is one more point to be noted. So far, what we mentioned, that in projection 3D points are mapped to 2D. The implication is that we are removing the z or depth component. However, it may be noted here at this point that while we implement the pipeline, this depth component is actually not removed. And why that is so? One operation that we perform in this fourth stage is called hidden surface removal. We will talk about this operation in details in a later lecture. The point to be noted here is that this operation requires depth information. So, the depth information after projection is actually not removed. Instead, this original depth information is stored in a separate storage, which is called the z buffer or the depth buffer. So, we are actually not removing the depth information, although we are performing a projection. Instead, we are keeping it stored separately in the z buffer or the depth buffer, and this information is required to perform a later operation called hidden surface removal, which gives us realistic effect in an image. So, that is in short what we do during projection and how we project from a world coordinate scene to a view plane. Now, there is one more stage. Let us go to that stage, that is mapping from this view plane to a viewport on the device space. So far what we have discussed, we discussed steps to transform a point in world coordinate to a clipping window on the view plane. That means, a region on the view plane on which we are projecting the objects that are part of the view volume. Now, also we have shown that this is typically the near plane of the canonical view volume. So, this is our window or clipping window. We can assume that for simplicity that the window is at 0 depth or z equal to 0, that is just for simplicity, although in general that is not an absolute requirement. It may also be noted that we are talking of canonical view volume, that is x and y extents must be within a fixed range irrespective of their actual position in the world coordinate scene. And because of this reason, where we are restricting everything within a fixed range, these canonical view volumes are standardized, and the clipping window that is defined on the near plane of the canonical view volume is often called a normalized window. So, here we are dealing with a normalized window where the extent of values are to be within a predefined range. Now, this view plane is actually an abstract concept. So, accordingly the clipping window is also an abstract and intermediate concept. We cannot see it. What we get to see on the screen is something different. The points that are there on the clipping window are to be shown on the screen, but the scene that is there in the window need not occupy the whole screen. For example, here suppose this outer rectangle define a whole scene, out of which we have projected this part defined within the clipping window. Now, this part can be displayed on any region of the screen and can be in any size. Now, the region on which this part is displayed on the screen is called the viewport. So, we have two concepts here, window which is same as the clipping window, which is normalized, and the objects are projected on this window, and we have the other concept viewport, which is defined in the device space with respect to the screen origin and dimension. So, this viewport refers to a region on the device space where this projected image needs to be shown. Now, this region can be at any location on the space, device space, and can be of any size irrespective of the size of the clipping window. So, what we need? We need to map from this window to the viewport. So, it requires one more transformation to transfer the points from the window to the viewport. So, let us see how we can perform this transformation. So, what we want, suppose this is our window and this is our viewport. Note that here we are not using this normalized range, we are formulating the problem in a very generic sense where this Wx and Wy can take any value. So, Wx, Wy is a point on the window and we want to map it to a point on the viewport Vx Vy. So, how we can do that? The first thing is that we have to maintain the relative position of this point with respect to its boundaries. So, same relative position has to be maintained in the viewport. So, if we want to maintain that, then we get relationships like the one shown here between the window dimensions and the viewport dimensions. Now, this expression can be simplified in this form. So, we can represent the x coordinate of the point in the viewport in terms of the x coordinate of the point in window and these two constants which are defined here in terms of the window and viewport sizes. Similar relationship we can form between the y coordinate of the point in the viewport and the y coordinate of the same point in the window by again forming the relationships first between the y coordinates and then simplifying and rearranging to get this relationship where V y is the y coordinate of the point in the viewport, W y is the y coordinate of the point in the window and these two are constants defined here in terms of again the window and viewport sizes. So, using those expressions we can actually form the transformation matrix as shown here. So, this is the matrix to transform this window point to the viewport point. And we will follow the same rule, that is to get the transformed point we will multiply the original point with the transformation matrix as shown here. Note that here again we are dealing with homogeneous coordinate system. Since these are 2 dimensional points, so we have 3 element vectors and 3 by 3 matrices. And at the end we need to divide the obtained coordinates here with the homogeneous factor as shown here to get the transformed points. The approach is similar to what we have seen earlier. So, that is the basic idea of how to transform from a point in the window or the clipping window to a point in the viewport, which can be anywhere on the device space. Now, let us try to understand the concepts that we have gone through so far in terms of few illustrative examples. So, in our earlier lecture we have come across this example where we mentioned one object shown here and a camera position, view of direction, everything has been mentioned and we computed the transformed center point of the object in the view coordinate system. So, we will not go into the details of how we calculated that again. Let us just mention the transformed point, that is 0 0 minus 1, that we got after applying this viewing transformation. Now, let us assume that the view plane is located at z equal to minus 0.5 and we want parallel projection. So, what would be the coordinate of the object center after the projection, assuming that the view volume is sufficiently large to encompass the whole transformed object. So, our parallel projection transformation matrix is given here and we know D is 0.5. So, this is our parallel projection matrix. So, if we use this matrix and perform the matrix multiplication here, the projection matrix and the point vector, then we get this point as the projected point on the view plane. Now, here since the homogeneous factor is 1, so our point is directly obtained. Now, let us consider perspective projection. Earlier we considered parallel projection. What will happen if we now consider a perspective projection with the same view plane? So, what would be the new point after projection? So, the transformation matrix for perspective projection is shown here. We know the value of D. Replacing D in this, we get our projection matrix, and with this matrix what we do? We multiply it with the point vector as before, as shown here. So, after multiplication we get this transformed point in homogeneous coordinate system. Now, note here that the homogeneous factor is not 1. Earlier I mentioned that in projection, particularly perspective projection, we get homogeneous factors that are not 1. So, there we need to be careful in concluding the final transformed point. We have to divide whatever we got with the homogeneous factor. So, after division we will get this point, or this is the final point that we get after perspective projection applied on the central point. So, we have performed projection. Now, let us try to see what happens if we want to perform this window to viewport transformation. Now, let us assume that we projected the point on a normalized clipping window and this projected point is at the center of the normalized window. Now, we are defining a viewport with a lower left corner at 4,4 and the top right corner at 6,8. So, that means if this is our viewport, then the lower left corner is this one, this is 4,4 and top right corner is 6,8. So, if we perform a window to viewport transformation, then what would be the position of the point, same central point in the viewport? Let us try to derive that. Now, we already mentioned that the clipping window is normalized. So, the values or the extents of the window are fixed. and we get these values. So, this is between -1 to 1, and again this is also between -1 to 1. So, we get these values, and from viewport specification we can see that this is 4 4. So, this 4 and this is, so if this point is 6 8, then this must be 6, this must be 8. So, we get these values. So, next we simply replace these values in the transformation matrices that we have seen earlier. We first compute the constant values Sx, Sy, Tx, Ty by using those values that we have seen earlier to get these results. Sx is 1, Sy is 2, Tx is 5 and Ty is 6. So, the transformation matrix can be obtained by replacing the Sx, Sy, Tx, Ty values in this original transformation matrix, which gives us this matrix. So, this will be our window to viewport transformation matrix. Now, once we obtain the transformation matrix, then it is easier to obtain the transformed point in the viewport by multiplying the transformation matrix with the point vector to obtain the transformed point in homogeneous coordinate. Now, here again the coordinate factor is not 1. So, we have to divide these values with the homogeneous factor as shown here and here, which eventually gives us the point 5 6. So, this will be our transformed point after we apply window to viewport transformation. So, this is how we get a transformed point in the viewport. Now, in this example you probably have noted that we have defined viewport irrespective of the window description. We can define it anywhere in the device space. What we need is basically a transformation. Also, you probably have noted that the viewport size has nothing to do with the window size. Window is normalized, whereas the viewport is not normalized. So, we can define any size by specifying its coordinate extents, and through mapping we get the transformed point. So, this gives us flexibility of placing the projected image anywhere on the screen with any size. So, in summary, what we have discussed so far are 3 substages of the viewing pipeline stage. So, these 3 substages are view transformation, projection transformation and viewport transformation. Just to recap, so these 3 substages are used to simulate the effect of taking a photograph. So, when we take a photograph, we look at the scene through mechanism provided in the camera. So, that we mimic by performing the viewing transformation. We transform the world coordinate scene to a 3D view coordinate system, which is actually equivalent to watching the scene through the viewing mechanism of the camera. Then we take a photo, that means we project it on the view plane, that is done through projection transformation, and finally we display it on the screen, which is of course not part of the photograph analogy, but we do it in computer graphics. So, that stage is mimicked with the use of window to viewport transformation. This transformation is required to have the flexibility of displaying the projected image anywhere on the screen and with any size, irrespective of the size of the clipping window. In the fourth stage, apart from these three substages which are related to three types of transformations, there are two more operations that are done. We already mentioned it in this lecture. One is clipping, one is hidden surface removal. So, these two operations we will discuss in our subsequent lectures. Whatever I have discussed today can be found from this book.